So in the last class, we have seen the isothermal expansion of an ideal gas. And these are all the things we have seen already. So this is where we stopped in the last class. The isothermal expansion of an ideal gas, we have to find out the values of Q, that is the heat supplied, W, the work done, and then delta U, the internal energy change, and then the delta H, enthalpy change. And isothermal means constant temperature. When the temperature is maintained constant, the process is called isothermal. So when no heat energy is lost or gained by the system, so temperature is maintained constant. So what actually we are doing is, when the system loses its heat content, we supply the heat content and we maintain the temperature constant. Suppose if the system is compressed, heat is generated and the generator heat is allowed to dissipate, and hence the temperature is maintained. So in these conditions, U remains a constant. Internal energy remains constant. So delta U is equal to 0. And then delta H, you know, it is delta U plus P into delta V. So that P into delta V, according to ideal gas equation, can be written as delta N RT. So delta N RT, R is already a constant, and the temperature, there is no change because this is an isothermal process. So delta U is a 0, and as it is a closed system, there cannot be change in the number of moles of the gaseous substance which is inside the cylinder. Therefore delta N is a 0. As everything is a 0, delta H is also 0. So the work is done at the expense of the heat absorbed. So expansion, the gas gets cooled down and the heat is supplied to maintain delta T 0. And compression, heat is generated and the heat is dissipated and the delta T is maintained 0. So work is done accordingly, whether the temperature is absorbed or temperature is liberated, work is done accordingly. So the magnitude of Q or W depends upon the reversibility or the irreversibility of the process. And this is all we have already seen. And this is also we have seen the maximum work done. The maximum work is done when the process is reversible, and the work done is 0 when the process is irreversible, that is the external pressure is equal to 0. So the magnitude of work done depends upon the magnitude of the external pressure. Actually, the statement is made like this: the condition for maximum work coincides with that for thermodynamic reversibility. Now, adiabatic expansion, this is what we are going to see today. Adiabatic expansion, condition is Q is equal to 0. That is, heat supplied is 0. You should compare the isothermal processes and the adiabatic processes. In isothermal process, temperature is maintained constant. In order to maintain the temperature constant, Q has to be supplied or Q has to be taken off from the system. You assume a cylinder which is fitted with a frictionless, massless piston, and the piston moves up and expansion is taking place. During expansion, the gas loses its temperature. There is a drop in the temperature. But in isothermal process, there should not be any change in the temperature. Temperature change should be zero. So what we are doing, we supply heat energy so that the temperature is maintained constant. So Q is supplied. Suppose the piston is compressed, then the gas molecules are enforced to come closer. So temperature is generated. The temperature of the system increases. In order to bring the temperature down so that the delta T can be zero, the piston is cooled down. In such cases, the Q is taken out. So the setup for the isothermal expansion or compression should be in such a way that the energy exchange is much faster. That is why the cylinder is made of a highly thermal conducting material. So the temperature has to come out or go in across the walls of the cylinder. So the wall material has to be highly thermal conductive. But in the case of adiabatic expansion, no heat should enter into the piston, into the system, or no heat should come out of the system. So what will happen? The Q is equal to 0. In order to achieve this condition, the material of the system should be highly insulative so that no heat enters. See, in the case of isothermal processes, the system has to be highly thermal conductive. But in the case of adiabatic processes, the system has to be highly insulative. So Q is equal to 0 in the case of adiabatic expansion. But according to mathematical expression of the first law of thermodynamics, delta U is equal to Q plus W. In this case, Q is equal to 0. So delta U is equal to W. So what is this? Work is done at the expense of the internal energy of the gaseous substance present inside the system. Suppose if you consider the expansion, the system is doing the work on the surrounding. That is expansion. So during expansion, there is a decrease in the internal energy. Therefore, the temperature decreases. As delta U is negative, work done is also negative. You know what is negative? Negative means the work is done by the system on the surrounding. For compression, delta U is positive. The work done is positive. So it is, the work is done at the expense of the internal energy of the gas. When the W is positive, the surrounding is doing the work on the system. So internal energy increases. But what is the relation between internal energy and the temperature? Look at this equation. Delta U, that is change in internal energy with the temperature at a constant volume condition, it is CV. So this equation can be written as du is equal to CV dt, or delta U is equal to CV delta T. Similarly, if you want to measure the enthalpy change in this process, H is equal to U plus PV, and if you introduce delta, delta H is equal to delta U plus P into delta V. I've already told you delta P into delta V can be written as R into delta T. So delta H is equal to what is delta U from the previous equation? It is CV into delta T. And then this becomes R into delta T. Now the delta T is a common, so that can be taken out. So CV plus R. Okay, listen. So CV plus R. We have already seen Cp minus Cv is equal to R. So Cv plus R is Cp. So delta H is equal to Cp delta T. So these two equations are very important. So when you discuss the adiabatic expansion of an ideal gas, the internal energy change is equal to the heat capacity of the gas at a constant volume condition into the temperature difference, and the enthalpy change is equal to the heat capacity. So it is so delta U is equal to heat capacity at a constant volume into temperature difference, and the enthalpy change is the heat capacity at a constant pressure into temperature difference. So the next slide, this you have to little bit concentrate. So what is this work done at a constant volume condition? Work done is delta U, which is equal to CV delta T. So the magnitude of delta U, delta H, and W, they depend upon the magnitude of delta T. But delta T actually depends upon the nature of the process. If the process is reversible or irreversible. So look here, actually at a constant volume condition, there is no work done because work itself is expansion or change in volume. But we want to equate so that we can arrive at the various temperatures at various volumes. Watch very closely. The delta U is equal to W. W is equal to minus P into delta V in the case of expansion. So watch carefully here, the network is a little bit interrupting. So the delta T depends upon the nature of the process, whether it is reversible or irreversible. And delta U is directly is equal to W, which is equal to minus P into delta V. Now, delta U, the same delta U is equal to CV delta T. Now, CV delta T is equal to minus P delta V. Or this can be written as CV dt is equal to minus P dV. Minus P is nothing but RT by V. According to ideal gas equation, PV is equal to RT. So P is equal to RT by V. That is what is substituted here. This is CV dt is equal to minus RT dV by V. Actually, it is minus RT by V dV. So what I am doing, CV, I am taking the temperature on the right hand side to the denominator of the left hand side. So it becomes a CV dt by T is equal to minus R dV by V. So this particular part can be written as CV d ln T 1 by t. On integration, it becomes ln t. On the right hand side, minus r differential of ln v. 1 by v becomes ln v. ln means natural logarithm. When you integrate both sides, this is what you are getting. Cv d ln t is equal to minus r d ln v. So the differential can be changed into the application of upper and lower limits. So what happens? Cv ln t2 by t1 is equal to minus r ln v2 by v1. I am applying the upper and lower limits. So it is volume 1 at temperature 1. It is volume 2 at temperature 2. So Cv ln T2 by T1 is equal to minus R ln V2 by V1, which is equal to that minus is taken off by changing the numerator into denominator and the denominator into numerator. So what happens? It is equal to minus is taken off is equal to R ln V1 by V2. Now you can relate ln T2 by T1, the Cv on the left hand side is brought to the right hand side in the denominator, which is equal to R by Cv ln V1 by V2. Now look here, what is R? Cp minus Cv is R. So Cp minus Cv divided by Cv, what happens? Cv by Cv becomes 1, whereas Cp by Cv becomes gamma. See, Cp by Cv is gamma. So this entire term becomes gamma minus 1 ln V1 by V2. So taking off the logarithm by integration, what you are getting is T2 by T1 is equal to V1 by V2 whole power gamma minus 1. So T1 by T2 is equal to V2 by V1 whole power gamma minus 1. That is what is written here. T1 by T2 is equal to V2 by V1 whole power gamma minus 1. If you want to understand, I want to tell you once again, watch closely. Cv dt is equal to minus P dV. In the place of P, I am substituting RT by V. From PV is equal to RT. So Cv dt is equal to minus RT dV by V. I am taking this T on the other side. This method is called variable separable method. All particular variables are brought to one side of the equation. See, all temperature dependent variables are brought here. Or volume dependent variables are brought over here. So dt by T, dV by V. So when you integrate, you are getting Cv differential of ln T. This is an integration procedure. This side minus R differential of ln V. When you apply the upper and the lower limits T1, T2, it is the final temperature by initial temperature. The final volume by initial volume. So Cv ln T2 by T1 is equal to minus R ln V2 by V1. The minus sign can be taken off when this V1 and V2 are interchanged. So taking the Cv the other side, ln T2 by T1 is equal to R by Cv ln V1 by V2. R, you know, it is a Cp minus Cv. So Cp minus Cv divided by Cv. This Cv and this Cv will form 1. Cp by Cv will form gamma. So ln T2 by T1 is equal to gamma minus 1 ln V1 by V2. So I can write T2 by T1 is equal to V1 by V2 whole power gamma minus 1. Because see, whatever comes before the logarithm, you are taking the anti-log and you are making this equation. Anything that is before here will go to the power. That is the normal convention. So T2 by T1 is equal to V1 by V2 whole power gamma minus 1. If you want to change T1 by T2, you change V2 by V1. So T1 by T2 is equal to V2 by V1 power gamma minus 1. So this is the equation. Now, you look here. I want to find out the relation between temperature and the pressure using the same equation. See, in the previous equation itself, we have seen T1 by T2 is equal to V2 by V1 whole power gamma minus 1. Now, what is V2? It is RT2 by P2 because P2 V2 is equal to RT2, ideal gas equation. P1 V1 is equal to RT1. Actually, this is supposed to be 1, RT1. So V2 is equal to RT2 by P2. V1 is equal to RT1 by P1. So V2 can be written as RT2 by P2 divided by V1 can be written as RT1 by P1. Actually, it is multiplied by the inverse. So it becomes RT2 by P2 into P1 by RT1. R and R can be cancelled off. And what you are getting here is T2 by T1 whole power gamma minus 1 into P1 by P2 whole power gamma minus 1. Already on the left hand side, we have one T1 by T2. So this can also be brought to the left hand side by inverting. So T1 goes up, T2 comes down. So it is a T1 by T2 multiplied by T1 by T2 whole power gamma minus 1. So when you multiply two factors like this, the power has to be added off. So here it is T1 by T2 whole power 1, actually 1 is there, multiplied by T1 by T2 whole power gamma minus 1. So when you add 1 plus gamma minus 1, the minus 1 vanishes. Minus 1 and plus 1 will get cancelled off. And finally, what you are getting is T1 by T2 power gamma, which is equal to P2 by P1 whole power 1 minus gamma. Or it is a P1 by P2 gamma minus 1, which is simply interchanged as P2 by P1 whole power 1 minus gamma. So this is a volume and the temperature and the pressure and the temperature in the case of adiabatic expansion and compression are evaluated. Now you look here, in the case of irreversible adiabatic expansion, in the irreversible adiabatic expansion, external pressure is 0. Work done is external pressure multiplied by volume change. So work done is 0. And also, as work done is 0, W is equal to delta U in the case of adiabatic process. So delta U is 0. The temperature change is also 0 because there is no change in the internal energy. There is no Q enters into the system. So Q is equal to 0. So delta T is equal to 0. As delta U is 0, delta T is 0, W is 0, delta H is also 0. So for an ideal gas, internal energy is a function of a temperature. As the internal energy is a function of temperature, as there is no change in the temperature, there is no change in the internal energy also. But you can think of one more expansion, which is called the intermediate expansion, which is neither reversible nor irreversible. Normally, in the irreversible expansion, we assume that the external pressure is 0. But in the case of intermediate expansion, we have a certain amount of external pressure which is not infinitesimally lower than the internal pressure. At the same time, which is not a 0 to have a large difference between the internal and the external pressure. It has a definite value. In such cases, we say the work done, which is minus, as the system is doing the work on the surrounding, as minus W is equal to external pressure multiplied by V2 minus V1, which is the delta V. So that is equal to the delta U, which is CV into T2 minus T1. So these two equations can be related like this. P external into V2 minus V1 equal to minus CV T2 minus T1. So CV T2 minus T1 is equal to P external V1 minus V2. Just I have interchanged the volumes to change the sign. So CV T2 minus T1 is equal to P external, which can be written in terms of pressure as RT1 by P1 minus RT2 by P2. Therefore, this is equal to R can be taken off as a common factor, R into P external into taking the denominator a common factor P1 P2, it becomes R P external T1 P2 minus T2 P1 divided by P1 P2. So this is about the irreversible adiabatic expansion. So